Good morning, I am Renu Sharma, Assistant Professor, EC Department. Now today we will start with the next part of Unit 2. Now this is related to deriving equations for FM wave with single tone modulation. So first we will discuss what is single tone modulation. Single tone modulation means that in the message signal there is only one frequency component present. In case of multiple tone, there are more than frequency components present in the input signal. Now this is the carrier signal that is denoted by that can be shown by this equation, that is AC cos omega Ct, where carrier frequency is given by omega c is equals to 2 pi fc. Then the modulating wave is given by this equation, that is am cos omega mt. So this is the single tone frequency. Single tone frequency means only one frequency component is present. Next is the modulating frequency, that will be given by this equation, that is omega m is equals to 2 pi fm, and that can be written as radians per second. So that will be the unit of omega m. Now next we will see the frequency deviation. Frequency deviation is denoted by delta f, whose formula is kf into am. Now what is kf? Kf is the frequency sensitivity or the deviation sensitivity. Its unit is hertz per volt. This is nothing, this is a kind of proportionality constant. Now this will be is equals to kf into m max minus m minimum divided by 2 into 2 pi. Now next parameter is modulation index, which is denoted by beta delta f upon fm. Now when we are considering the FM wave, we have to consider a parameter, that is instantaneous frequency, which means that the frequency is changed from carrier frequency and the resulting frequency will be the instantaneous frequency. Whereas in case of PM, phase modulation, we have to consider a parameter, that is phi I, instantaneous phase angle. So in this, since it is a FM signal, we have to consider this Fi. Fi is equals to Fc plus Kf into Am cos omega mt. So this will be Fc plus delta f into cos omega mt. So we can also remember the equation of the standard FM, which is AC in bracket cos omega Ct plus Kf integral mt into dt. So after considering these parameters that I have discussed, the resulting equation will be this one for the single tone modulation. Phi fmt is equals to AC cos omega Ct plus beta into sin omega mt, where beta is the modulation index of the FM signal. Now next is the first block can be a linear time invariant operator, that is LTI operator, and it need only be invertible so that we can recover the signal mt. So in general we have ht is the unit impulse response. So phi ga mt is equals to a cos omega ct plus integral mt into ht minus alpha d alpha. So for phase modulation, ht is equals to kp into delta t. For frequency modulator, ht will be equals to kf into ut. So ut means it is a unit step and del t it is a impulse function. So we shall focus on FM in this course, less on PM. So FM is more important and it is widely used as compared to the PM. Now we are going to calculate the average power of an FM wave or PM wave. The amplitude A is kept constant in PM or FM. RF power does not depend upon the frequency or the phase of the waveform. So phi FM or PM can be written as A cos omega Ct plus F K comma mt. So that is a function defined of two parameters K and mt. Mt is the message signal, K is the constant, that is frequency sensitivity kf. So the average power from this particular equation can be written as a square by 2 or ac square upon 2r. Now if the r is the resistance, if the resistance is not given, we can consider it as 1 ohm, and if it is given, so then you have to consider that in this formula. Next is the ac square, that is the amplitude of the carrier signal. So this is the result of FM and PM signal being having constant amplitude. Now next important topic related to the AM DSP with carrier, that is the spectrum, that phasor diagram that we have to consider. So since in case of AM, three frequencies are transmitted. First one is the carrier frequency, next one is the upper sideband, and other one is the lower sideband. So these are the three frequencies that we have to transmit in case of amplitude modulation or DSP with carrier. That is the simplest kind of amplitude modulation. So according to that, this is the phasor diagram. Like omega c rotates faster than omega m because omega c is having higher frequency as compared to the frequency of the message signal. So this will be the center frequency, this will be the upper sideband to the right hand side, and this will be the lower sideband frequency to the left hand side of the center frequency omega c. Corresponding to that, you can see that this is cos omega ct, higher frequency. This is cos omega mt, that is of lower, very low frequency, and this will be the modulated signal. Now if you can see that if I am going to join this, this will be known as envelope of this signal, that is cos omega m t. So this particular waveform is used for the demodulation of the AM signal. Now next is phasor interpretation of AM with carrier. So VUS is nothing, it is the voltage of the upper sideband, VLS is the voltage of the lower sideband, and VC is the voltage of the carrier signal. So this is known as V minimum, this is known as V max. So before seeing this particular waveform, you should remember that there are three cases. When I have taught you this amplitude modulation, there are three cases: when m is less than 1, when m is equals to 1, and when m is greater than 1. So for all the three cases, this is the case for m is greater than 1. This is known as over modulation. And what happens over here, that whatever you are seeing that it is above the origin, this crosses the origin and there will be 90-degree phase shift in the resulting waveform. So that causes loss of information. So that is not required. M is greater than 1. Ideally, we require this m is less than 1. This is the case for m is less than 1, where this V minimum does not touches the origin. In case of m is equals to 1, this will be the waveform. So you can see that it just touches the origin. So this is the case for m is equals to 1. This is the case for m is less than 1 under modulation. This is ideal situation, this is practical, and this is not required. So when we are going to calculate the value of V minimum and V maximum from this particular diagram, so you can see that V minimum is voltage in the carrier minus upper sideband voltage minus lower sideband voltage. In case of this one, there will be V max, this is voltage of the carrier signal plus voltage of upper sideband and voltage of the lower sideband. So this is how the phasor diagram will looks like. This is the negative part of V max, this is the negative part of V minimum. Now next is a very important numerical, that is to sketch the FM and PM waveform for the modulating signal, that is MT. So the constants Kf and Kp, according to this particular waveform, only this waveform is given to you. You have to draw this waveform and you have to draw the PM signal from this particular message signal. So what is given in the numerical is the constants value, that is Kf and Kp. Kf value is 2 pi into 10 to the power 5 and Kp value is 10 pi respectively. Then carrier frequency is given, that is 100 megahertz, and MT signal is given, this one. So if you remember that from the standard equation for FM and PM, integration is used in the FM equation and the differentiation, if you are going to differentiate the FM signal, you are getting the PM signal. So what it is written over here, that empty is there, we have to differentiate this particular waveform. So the differentiation of sawtooth waveform or the ramp function is the unit step signal. So this is somewhat like unit step. Now in case of FM, the instantaneous frequency is given by this equation, Fi is equals to Fc plus Kf upon 2 pi into Mt, which is equals to, this value is given to you 100 megahertz plus Kf is also given divided by 2 pi into Mt. Mt amplitude will be 1. So M max is 1, M minimum is minus 1. So you can calculate both the values and corresponding to that you can draw the waveform. In case of PM, the same equation will be used, but instead of Kf you have to use this Kp, and instead of Mt you have to use differentiation of Mt. So by putting the value, we are getting the values, that is for the minimum instantaneous frequency and maximum frequency, that is 99.9 megahertz is the minimum one and maximum will be 100.1 megahertz. So that is the case for FM and PM wave. Now next is FM and PM wave. Again we have to consider, but here the value is different, that is Kp value is pi by 2. The same numerical will be there. So since Mt switches from +1 to -1 and vice versa, then FM wave frequency switches between 99.9 megahertz to 100 megahertz, which means 100 megahertz is the center frequency. This is 100.1, this is 99.9 megahertz. So this will be the Fc, this will be Fc plus delta F, this will be Fc minus delta F. So you can easily calculate the value of delta F from this particular waveform. Our next numerical is sketch the FM and PM wave for the constants. Now the previous one is for PM, now this is for the previous one for the FM, this is for the PM case, where the carrier frequency is 100 megahertz. So this will be the differentiation of the message signal, that is denoted by M dot T. This will be 5 PMT. Now this will be 100 megahertz of the PM wave. Now the same equation is there, but we have to use Kp and M dot T instead of Kf and Mt. So instantaneous frequency will be equals to Fc plus Kp upon 2 pi into differentiation of message signal, which is equivalent to this equation. So this is carrier PM, why a digital signal, and its digital signal, it is the phase shift keying, that is PSK, because digital data is represented by the phase of the carrier wave. So according to this particular equation, the 5 PM wave can be written as A cos omega Ct plus Kp into Mt, which is equals to A cos omega Ct plus pi by 2 into Mt, where 5 PM is the phase of the PM signal. This is the A sin omega Ct. When Mt is equals to -1, when Mt is equals to +1, then this will be minus A sin omega Ct. Now we have to see that how we are going to select the FM station. So you are very familiar with the FM system, means we are listening the FM radio. So in case of FM radio, the frequency variation that is standard, that will be from 88 megahertz to 108 megahertz, which means there are different channels which exist, like 97.3 megahertz, 93.5 megahertz, 102, 104, 104.8. So these are the different stations that are available on which you can listen the FM radio. So 100 stations are there, and the spacing between each station is 200 kilohertz, which means, let's say this is 88 megahertz to 108 megahertz frequency range is there, and there are 100 stations. So in between these 100 stations, this is first, this is second, this is third, this is fourth, and so on. So in between this there is 200 kilohertz of guard band is being provided. So this guard band is basically been introduced between the two channels, so that any kind of spreading of the signal will not going to distort the information from the two signals, basically to reduce the interference. So consider tuning in an FM radio station. What allows your radio to isolate one station from all the adjacent stations are there, like this one is 90.3 WHID in this particular area. So these are the areas where different frequency bands are allocated. Now next is specification for commercial FM transmissions. So this is a table which is showing the different service types, like this is for the commercial FM radio system, this is for the television sound analog, then this is public safety, that is police, fire, ambulance, taxi, forestry. This is amateur, common emitter class A, and business band radio. So these are the different service types which are provided. Now these are the different frequency bands which exist, like this is 88 kilohertz to 108 megahertz. This is 4.5 megahertz above the picture carrier frequency. This is 50 megahertz. This is for 216 to 470. So this is the range. These are the corresponding channel bits, channel bandwidth. This is maximum deviation that is allowed. So as you can see, this one, this is the standard case of FM radio, where the frequency band is from 88 to 108 megahertz. This is channel bandwidth, that is 200 kilohertz. Maximum deviation is 75 kilohertz, and highest audio frequency that is allowed is 15 kilohertz practically. Now next is phasor construction of an FM signal. So in the earlier case we have discussed about the AM phasor construction. Now we have to see for the FM case. So in this particular case we are constrained by constant amplitude for both the FM and PM signals. This is nothing, it is the NBFM case. So the next is showing the animation of this. So this is the center frequency. Now at every point this will be changed. So this is how we have to draw the FM signal. Now next comes the direct generation of the FM signal using a voltage control oscillator, that is VCO. So the input signal to this voltage control oscillator is empty. This is the voltage control, that is empty, which is provided over here. Varactor diodes are used, like this is the varactor diode 1, this is varactor diode 2, so this is D1 and D2. This is inductor, capacitance, variable capacitance is there. This is inductor, variable inductor is connected, and this is FET. So this is how we have to draw the direct generation of the FM signal. Now the oscillating frequency is equivalent to 1 upon under root LC, or the resonant frequency of this particular signal, that is Fi is equals to 1 upon 2 pi under root LC. So C equivalent means if there are more than one capacitance are used in the circuit, then you have to calculate the C equivalent, if it is connected in series or parallel. So you have to calculate the C equivalent and put it in this formula. Next one is the indirect generation of the FM signal using a multiplication. In this method, the narrowband FM is first generated, and then the frequency multiplier is used to increase the modulation index. So basically, why this indirect method is known as indirect? In this case, firstly, the narrowband FM signal is produced, and by using the combination of different frequency multipliers, this NBFM is converted to wideband FM. So basically what we are doing, we are increasing the modulation index. When we increase the modulation index, when it is greater than 1 or it is greater than 0.3, then it comes in the range of wideband FM. So what we are doing in the indirect method. So this is the message signal empty which is provided in this NBFM. The output will be a narrowband FM signal, then a series of means different frequency multipliers are connected in cascade, and the output will be a wideband FM. A frequency multiplier is used to increase both the carrier frequency and the modulation index by the integer that is denoted by capital N. Now, this is the Armstrong indirect method, very important topic related to the indirect FM generation. So, as you can see, this is NBFM generation. Its input will be an signal that is FM. Carrier frequency is 200 kilohertz. Its deviation is 25 hertz. So, this is a very standard numerical, or you can say the description of Armstrong method. The output of this will be a carrier frequency and NBFM. This is applied to one of the multiplier whose multiplication constant is 64. So, after multiplying this input frequency by 64, we are getting this value, that is FC2 and delta F2. This is applied to a mixer. This is nothing, it is a mixer. This will act as a summation of the two input frequencies or the subtraction of two input frequencies. This will be the local oscillator frequency. So, this 12.8 will be subtracted from this. So, we will get this 1.9 megahertz of frequency FC3 and delta F, there is no change. So, this is passed through a band pass filter. Now, after that, there is a second multiplier whose multiplying constant is 48. Now, this FC3 is multiplied by 48. We are getting this 91.2 megahertz of frequency, and again this will be multiplied. So, we are getting this delta F4. So, this is the final frequency deviation. So, these are the numbers which are related to FM broadcast radio station. Now, next is generation of narrowband FM. So, how we are going to generate the narrowband FM? This is the very simplest kind of diagram. This is the message signal which is applied to this integrator. To this integrator, it is passed through a DSP-SC modulator, which is nothing, it is a product modulator only, which will multiply the two input frequencies, this one, and the output of this will be a KF. So, this will be the frequency sensitivity. This is frequency sensitivity, its unit is hertz per volt, and then the output of this will be applied to a summation. So, this is the very simplest kind of diagram for generating the NBFM signal. Now, this is for the narrowband PM signal. Now, as you can see from this particular equation, that is phi PMT is equals to A cos omega CT plus Kp into MT, where Kp is the phase sensitivity. Again, it is the proportionality constant or the phase sensitivity. Its unit is radians per volt. Corresponding to that, you can draw this particular diagram. Now comes the advantage of FM and disadvantage of FM. So, first we will discuss the advantages of FM. Now, first advantage is the resilient to noise. The main advantage of FM is a reduction of noise. So, this has a greater advantage as compared to the AM case, that is the amplitude modulation. Second one is resilient to signal strength variation. So, in the same way that amplitude noise can be removed, so too can signal variations due to channel degradation, because it does not suffer from amplitude variations as the signal level will vary. So, this is the case, because amplitude in this particular case FM, it is constant, we are not changing the amplitude. So, whatever problem is there due to the change in the amplitude, it will be removed. Now, does not require linear amplifiers in the transmitter and enables the greater efficiency. Now, these are some of the disadvantages, like it requires more complicated demodulator and sidebands extend to infinity either side in the case of WBFM. So, this is related to FM. Thank you.